Hello, Calculus and Vectors class, and welcome to your very first lesson for the calculus portion of the course. Now, you're going to find that this is a complete departure from everything we learned in vectors. We're pretty much starting from scratch again. We're going to start with some knowledge that you will have learned in advanced functions, hopefully. If not, then you're going to relearn it right now, and we're going to use that as kind of a springboard into learning what we know today as calculus. But for right now, we're going to just focus on the building blocks and we're going to work our way into it. So our big goals today, we're going to connect the slope of the secant to the average rate of change. We're going to connect the slope of the tangent to the instantaneous rate of change. And we're going to calculate the average and instantaneous rates of change using the slope of the secants and the tangents. So we'll talk about more about what that means, but at the top of every lesson from here on in, I'm going to start putting our goals so that way you have kind of a sense of what our big ideas for each lesson are. So really quickly, before we start going into some calculations, let's do a bit of a review. Hopefully you learn these things in advanced functions. If not, you're going to learn them right now. So the first thing you should know is a secant. A secant, it connects 2 points on a function. A tangent connects it touches the function at a single point. And you're going to notice with a tangent, it just kind of passes along and just kind of kisses the function at that one point. And you'll notice if you draw on it correctly, then it should have roughly about the same angle on either side of your function. So now you know what a tangent is and a secant is. Let's talk about some problems that deal with secants and tangents. So let's talk about average rates of change. And we're going to start connecting that into our knowledge of secants and tangents once we understand it a little bit better. So hopefully you've seen this in advanced functions as well. All we're doing is when we see average rate of change, we're just thinking of the slope between 2 points or over a specific interval. So in example 1, it's asking us to consider the population of walleye fish over 10 years and calculate the rate of change over the 10 years. So essentially, all it's asking us in this problem is to look over that 10 years, so between year 0 and year 10, and trying to figure out the average rate of change. So first big idea that hopefully you'll keep with you for the rest of this course and beyond is when you see rate of change, always think slope. Slope of something. So we'll talk more about that over this course of this unit, but when we see rate of change, think slope. So we're going to start with our slope formula. Again, hopefully this is not anything new to you. So slope is delta y over delta x, or y2 minus y1 over x2 minus x1. In this case, we're measuring over those 10 years. So for our x2 minus x1, it's 10 minus 0. And for our y2 minus y1, it's 4,786 minus 3,000. When you do the math on that, you're gonna get 1,786 over 10, or get 178.6. But of course, we need to have some units on this. So to do that, we're going to look at the units for our y's and x's. For the y's, it's going to be number of fish, and the x is going to be years. And since we're doing y divided by x, it's going to be fish per year. So what that number represents is over the course of that 10 years, on average, we are gaining 178.6 fish every single year in our pond or in our lake or wherever we're measuring. So over 10 years, it's not super accurate. We can see from the graph, it goes up by different amounts each time. Looks like it goes up by 400 each time of the first time, and then by about 320, and then smaller amounts every single time. So it seems like that's not really a consistent growth over that 10 years. So it's not super accurate. So when we're looking over 10 years, not super accurate. Maybe if we were able to get in a little bit closer, it might help us a bit. So let's try an example where we're looking at a bit more detail. Example 2, the plug is pulled in a small hot tub. The table below gives the volume of water in the tub from the moment the plug is pulled until it's empty. So question A asks, does half the water drain in half the time? So let's compare. So first of all, you're going to notice that at time 0, there's 1,600. So if we're looking at half of that, that's going to be half volume at 0, which is equal to a half times 1,600, or 800. We're measuring in liters right now. So half the volume at the start is 800 liters, but let's compare. We're going over 120 seconds, so 60 seconds would be the halfway mark. And at that point, we have 400 liters. So the volume at 60, the halfway mark, is actually 400 liters. So what that means is that more than half the water drains in half the time. So more than half the water drains in half the time. So now, the first example, we just looked on average over the whole thing, and it was not accurate at all. Now we're looking at it at the halfway mark. We're taking this data and we're splitting it in half, and we're getting a bit of a clearer picture, but it's still not super accurate. We're still getting 400 liters versus 800 liters, which is quite a big difference. So let's take a look at this data in a bit more detail. So we're going to look at the rate of change between each time interval. I'm sure you guys are awesome with first differences already, so I've gone ahead and filled them in. And to find the average rate of change, we just need to find overall, we just need to divide that by the time interval here. So we're going up by 10 seconds. So every time we're just going to divide by 10, divide by 10, so on and so forth. And so that's going to become negative 25.6 liters per second, negative 23.3 liters per second, negative 21.1 liters per second, negative 18.9 liters per second, and so on and so forth. Negative 5.6, negative 3.3, negative 1.1. So that is kind of interesting. When we break it up over smaller intervals, we get very, very different numbers. So to answer these questions really quick, over 0 to 10 seconds, the average rate of change is negative 25.6 liters per second. For 50 to 60 seconds, it's going to be, negative 14.4 liters per second. And between 110 and 120 seconds, we get negative 1.1 liters per second. So let's talk about this data and let's see if we can figure out what this means. So from 0 to 10 seconds, our average rate of change is negative 25.6 liters per second. So what that means is that every single second between 0 and 10 seconds, on average, we're losing 25.6 liters per second. The negative means that we're losing, and 25.6 refers to the number of liters that we're losing every single second on average. Between 50 and 60, we're losing a little bit less. It's 14.4 liters per second because there's less pressure from the water above pushing it down the drain. And then at the very end, we're losing about 1.1 liters per second. So just by breaking up into smaller intervals, we're getting clear snapshots of what's going on every single 10 seconds. So the big takeaway from this, hopefully, is that every time you make your interval smaller, you're going to get a bit of a clearer snapshot. So just to quickly sum up here, the average rate of change for this problem, y2 minus y1 over x2 minus x1. And in this case, it's going to be the volume function at x2 minus the volume function at x1 divided by x2 minus x1. Now, graphically, what this looks like, I've taken all that data from our table there, and I've put it into a graph form. Now, I want you to take a look between 0 seconds and 10 seconds. And compare it to 50 seconds, 60 seconds, 110 to 120. Now we can see right just from that the slope of our secants is going to be quite different. We go from very steep negative to moderate negative to not steep at all negative. So the other big takeaway from this is that when you look at the graph, there's a connection between the average rate of change and the secants. So in fact, the average rate of change between the 2 points is the slope of the secant. So if you were to examine those secants, you'll actually notice that the average rate of change that we calculated above in B, C, and D, they actually line up with the slopes of those tangents, and they're actually the exact same thing. So that's our first big takeaway from this. A few things. Number one, our average rate of change, our secant, are essentially the same thing. And if we can make our average rate of change, if we can make the intervals as small as possible, we'll get much clearer snapshots of what's going on. So now that we've talked about that, let's talk about instantaneous rate of change. Instantaneous rate of change just refers to the rate of change specifically at one single point, how quickly something is changing at a specific point. So to do that, let's try another example and we'll talk about it really quick. So example 3, a decorative balloon is being filled with helium. The table shows the volume of the helium in the balloon at 3-second intervals for 30 seconds. So every 3 seconds, we're measuring the volume of the balloon. So let's try and examine this a little bit. So it's asking us to use the table to calculate the average rate of change, the slope of the secant for the following intervals. So part 1 says 21 seconds to 30 seconds. So to do that, we're going to take the slope, which is just the volume at 30 seconds, minus the volume at 21 seconds, divided by 30 minus 21. Our values up top can be found from the table. Volume at 30 seconds we see is 4,186.7. Minus the volume at 21 seconds is 1,436.0. All over 9. And that should be equal to roughly 305.6 centimeters cubed per second. Let's do the same thing for 21 seconds to 27 seconds. So same basic idea, except this time we're just going to change our data that we're using here. So instead of 30, we're going to go to 27, and 21 stays the same. So in this case, we have, I think it's 3,052.1 minus 1,436.0. And this time, it's 27 minus 21. So we're looking over an interval of 6 seconds. So we said, based on our knowledge from the last portion of the lesson, we should be getting a slightly more accurate snapshot of what's going on. So in this case, we have 269.35 centimeters cubed per second. And we're going to say it's roughly equal to that, just because we know we're rounding off a little bit. So now we're going to look at 21 to 24 seconds. So you're probably noticing, by the way, that every single time the 21 stays the same, but the second number, the end of our interval, is getting a little bit closer to 21. Our numbers are getting closer together. So hopefully as we do this, we get a slightly more accurate snapshot of what's going on. So this time we're going to take the volume at 24 seconds minus the volume at 21 seconds. Divide by 24 minus 21. So that's, according to our data, it's going to be 2,143.6 minus 1,436.0, all divided by 3 seconds. So we're measuring it over an interval of 3 seconds. And when you do the math on that, it's going to become 235.87 centimeters cubed per second. So if we measure over 9 seconds versus 6 seconds versus 3 seconds, we get drastically different snapshots of what's going on. And the smaller the interval we get, the more of a clear picture we get. So let's look at this problem in a slightly different way. I have the graph of the volume of the helium in the balloon. It's the same data points, just graphed. And I have our tangent line here. And normally we're not going to have these 2 points, but just because we're still trying to figure things out, I've added this point Q. So we have point P, that's the one that's right on the curve, and we have point Q. And what we're going to do is we're going to take those 2 points and we're just going to calculate the slope of the tangent. So that's going to be y2 minus y1 over x2 minus x1, which is going to be 1,436 minus 500 over 21 minus 16.5. That's going to be 208 centimeters cubed per second. Now, just to quickly reiterate again, the average rate of change between 2 points is the slope of the secant. But in this one, take a look. We have P and we have Q. Q is not on our curve, so it doesn't really count. We're just kind of using that to help us figure this out. At this point, we just have P on the curve, so this one's actually tangent. In fact, you can almost think of that as having 2 points right on top of each other, and we're trying to find the slope between those 2 points. But of course, we can't really do that because we don't know how to divide by 0. It doesn't make sense. So we're just going to kind of think about that conceptually right now, and then we're going to use some more complicated math to start working around that over the next few lessons. But for right now, this is the slope of the tangent. So now that we've done that, let's connect our information here. So the first thing it asks, what do you notice about the average rate of change and the time intervals from part A? So the first thing you should notice is that they get smaller. In fact, they're all going in the same direction. They're going from 305.6 to 269.35 to 235.87. So in fact, they're all going in the same direction and they're gradually getting smaller. And in fact, we know that as we get that time interval smaller, we're going to start getting closer and closer to the actual instantaneous rate of change at 21. So comparing the slopes of the tangents from part A to the slope of the tangent from part B, as the interval gets smaller, the slope of the secant approaches the slope of the tangent. So really, all we're doing, you should take a look again, 305.6, 269.35, 235.87. Essentially, we're just making our interval smaller and smaller and smaller until we get to 0, which is the slope of our tangent. The other way that you can think of a tangent, we're looking at the average rate of change over an interval of 0 seconds. It's kind of a weird way to think about it because, number one, we can't really measure something over 0 seconds. It's kind of impossible. And number two, we can't divide by 0 in the denominator, so it doesn't really make sense. But conceptually, that's the way I want you guys to start thinking about these types of problems, because as we do more of these problems, we're going to learn some methods in order to work around that dividing by 0 problem, which is going to help us to make a bit more sense. But right now, what you should kind of take away from this is as we get smaller and smaller intervals that we're measuring average rate of change over, we're getting closer and closer to finding the instantaneous rate of change. Thus, to find the instantaneous rate of change, we calculate the slope of the tangent. So that's pretty much it. Go do some practice problems, and I'll see you in 4.2.